All right, line L1, we're in learning task number 1, where we are going to be taking a look at single-phase AC grounding requirements. The first thing that you need to know before we start into this one, though, is careful. Okay, be very, very careful, because this was written back when the 2015 Canadian Electrical Code was still in effect, and then after the 2015 code was replaced by the 2018 code, there was some major changes to our Section 10. Some changes are actual things that have been taken out or added in. I'll note those when we get there. The bulk of the changes are going to be just ordering changes, where they have placed them and a little bit of rewording, but it's still going to be the same thrust. And we're just going to identify those as we go through. So have your code book out. Make sure that you are ready to go and identify and find these rules. Okay, let's start with the very first section that they have. So the very first one that they talk about is going to be sizing, and sizing of the ground conductor itself. Now the ground conductor, if you watched that review video, we took a look at fault current that is going to be traveling along the bonding pathway. The ground conductor carries little to no current ever. Practically speaking, it could be as small as a number 14 or a number 16. The problem with those is that those wires aren't very robust. There'd be a good chance that things would get broken, and then we would have chances that we're going to have an ungrounded system. As a result of that, the Canadian Electrical Code has required that we place a minimum size inside of there. In your book there, it says CEC 10.8.112. In reality, it is going to go and be CEC 10.114. Let me just roll down to that one. Over here. 10.114 states that the minimum size of grounding conductor shall be size not smaller than number 6 if of copper. Number 4 if of aluminum. I only highlight the copper one because it's rare that we are going to go and be number 4. It does say that I am also allowed to have a grounding conductor shall be permitted to be sized smaller than that prescribed inside of my sub-rule number 1. So what I'm talking about inside here, I'm allowed to go smaller, provided that it is not smaller than the current carrying conductors of the system being grounded. If I've got something that is going to be fed, with number 10s would be the smallest size service you could have, a 30 amp service. You would be allowed, but you'd have to get special permission. Most cases, you're never going to see anything smaller than this number 10 that we are going to have. The next section inside of your binders is going to go and deal with, hold on, let me just remove those arrows. It's a little bit weird trying to erase stuff inside of a PDF. It doesn't grab it quite the same, but oh well. Yeah, close enough. Okay. Next section inside of your PowerPoint over here talks about connections. This used to be a consideration. It is now no longer going to be a consideration, that it has to be substantial and non-reversible. Let me just talk about what exactly it is. That rule that's listed inside of there, 10.806.1, did get struck out of the 2018 Canadian Electrical Code. It no longer exists. You are now allowed to go and use split bolts. Before, you had to have something that was referred to as being substantial and non-reversible. That being said, we do still have to go and terminate grounding conductors together. Whether it's going to be for broken grounding conductors, whether it's going to be for tying multiple different types of system grounds together. And we got a couple of methods that are listed over here. Compression connectors, these things are also often referred to as C-taps. If somebody tells you that they want you to go and get C-taps, that's usually what they're going to be talking about. They're going to be made out of copper. They're usually going to have a little bit of antioxidant compound that's going to be, grouped inside of these things. You place your 2 wires, you shove them in sideways like this, and then you crimp them, and they go tight around like that. The other methodology is going to be what we refer to as exothermic welding, and this is going to be where we're going to have powdered aluminum and copper. And then we are going to go and have an igniting powder, and what happens is that forms a really violent and intensely hot chemical reaction. And so it forms molten copper. The molten copper starts out in the top part of what we refer to as the crucible or the mold. So we place these ones into that mold. This conductor would be running straight through. This conductor would get butted into that mold. We place all the powder inside there. We place the ignition system into it, and then we spark that thing up. It welds, and then it's going to be a poured copper connection that's going to be inside of those. It is referred to as CAD welding. just because it was originally made by this Cadwell Systems, and so they were the only ones that sold the components. So everybody was like, "Oh yeah, get a CAD welding kit," and stuff like that. So we still refer to it as CAD welding. We will see these inside of high voltage, in a lot of high voltage situations, as well as you'll see them inside of places like if you're working off of distributions for electric railways and things like that, where there's a lot of vibration, they don't want to have stuff coming apart. They'd rather do this because it's a proper welded type of connection. Talking about what's inside of the book there, they do talk about connecting together several grounding conductors from separate electrodes. And to give you a rule in there, it's CEC 10702 in the 2018 code book. It is actually going to be changed to 10104. We'll just go up to it. And it says, where there are multiple grounding electrodes at a building, they shall be, and this is an important part over here, separated by at least 2 meters from each other, and then interconnected with a conductor. So we have to keep them separated, but we do have to go and interconnect them. And in the case of a lightning protection system, interconnected in accordance with item B at or below ground level. So it has to be a buried conductor. The reason that they're talking about these things being interconnected yet 2 meters apart is simply for the fact that we generally have only 2 grounding electrodes at a building. Usually 1, but if we have got 2, it's going to be one that is going to be referred to as the lightning down rod. So tall buildings are going to go and have a lightning rod on the top. That lightning rod is going to have a conductor that's going to go all the way down that building, and then it is going to get brought down to a ground electrode. Okay, we will put a little plate in the ground right over there. Just because the taller something is, the greater the chance that that thing is going to go and conduct electricity. And rather than going and allowing that to happen, all over the place, we control the lightning. We give it a path so it can go and discharge through that. That would be my lightning down connector. What I'm also going to have inside of that building is my regular grounding system. And my regular grounding system is going to be attached to the neutral that's going to be inside of my system and of all of my electrical distribution. These two do need to be at least 2 meters apart. We sometimes have other ones for CAT TV or for telephone, but these are the most common ones that we would have. They want to keep them 2 meters apart because in the event of a lightning strike, we get mass amounts of current that are going to get dumped through here. And as a result of that, we're going to go and get what are referred to as step voltages. These are going to be rings of voltage that are around the outside. Now, past about, a meter and a bit, they don't really form anything that significant. However, if I would have kept these two together, tightly close together over there, what would happen inside of my building is that this lightning, instead of wanting to run all the way down this to where it's got this potential over here, some of it would divert into the building wiring system and run back down to that because it sees that it's getting ultimately back to that same point, and that same point is going to be easily accessible by just breaching our insulation. Insulation for NMD is only 300 volts. So we want to keep these things far enough apart so that we don't get any cross breaching anytime that we get that carried down through. That's the reason for that 2 meter separation off of those. That being said, we do have to connect them together at or below ground level. The reason that we are going to go and connect them together at or below ground level is that ultimately this whole Earth is going to be seen as being at the same potential. This just allows us to spread that whole thing apart, but it doesn't want to create the same path that's going to pull it through. That one, like we said, was going to be CEC 10104. That is going to go and talk about that. Okay, so our 2 types of connections that are inside of there are valid types of connections. They're no longer required. They're still considered to be the best case type of connections. You can also use split bolts when you are connecting stuff together. But the problem with split bolts is that they have to be done up tight and they can be removed. Somebody all of a sudden decides that they want to have a, couple ounces of pure copper to throw into the recycling fund. They just got to back that thing off, right? Those things go missing. These ones over here don't generally tend to go and do so. Let's talk about the grounding conductors itself. So inside of the Canadian Electrical Code, we are told about our grounding conductors. We're going to go to 10, and then we're going to go all the way over to 1112 over here. Not the sizing one, but the one about materials over here. And it says a grounding conductor shall be copper, aluminum, or other acceptable material. There are some places where we want copper. There are some places we could be using aluminum. And there are some places like, docks or things like that where you might need to have something that's going to be non-corrosive, stainless steels and zincs and things like that. And they are permitted to be insulated or bare. Now, what they're talking about is the actual grounding conductor that is going from the panel to the electrode itself. It does also spec that our grounding conductor shall be resistant to any corrosive condition existing at the installation, or it has to be protected against corrosion. So aluminum is not going to be resistant to corrosion when placed underground. This is the rule that is interpreted as, that anytime that we have got a conductor, a grounding conductor, that grounding conductor has to be copper. Over here, this copper grounding conductor. Here's my grounding electrode. The grounding conductor is always the conductor that is running through here up into the neutral itself. That is considered to be a grounding conductor. It goes directly between the neutral and the earth itself. I can have other smaller systems that I'm going to go and attach onto here. These are going to be defined as being separately derived systems inside of my Canadian electrical code, where I'm taking, my volta over here. I got a 120/240, and I'm going to go and feed 240 in onto one side of my transformer, and then out the other side, I'm dropping that thing down to, 120, down to 1224. Maybe there's a bunch of low voltage lighting, whatever is inside of here, it doesn't really matter. We go and run that out of that transformer to its circuit protection, etc. But then what I'm going to do is I need to go and ground that neutral that I have on that transformer. I am, in this case, allowed to go and use aluminum to take it up to here, connect those things together there with approved, connector and proper antioxidant inside of there. But that one could be aluminum because it is all within that dry indoor area. Okay, that's the only time that we're going to use aluminum is going to be inside dry indoor areas. Now, we will have some times where we might have multiple transformers that are going to be fed, single-phase transformers inside of multi-family residential, right? Where we've got apartment buildings and we're going to take high voltage to each floor, then we drop to a transformer and sub-distribute, so we don't have to go as far with our high amperage cables. That's a very common place where I'm going to have multiple grounding conductors that are all going to get carried down, from floor to floor to floor to floor to floor, all the way down to your main service inside of, the bottom level usually. That is then going to go and have the actual grounding conductor. And so you're going to go and have these aluminum conductors that are going to go from floor to floor. They're going to splice onto another one, and then they're going to go and bolt down to this one over here. The code no longer requires us to go and have something that is going to be substantive, that whole CTAPs or CADWELDs. However, in most cases, the inspectors will, because there's this danger that once again, if somebody gets access to that electrical room and removes that little splice, and these things happen, somebody needs a split bolt and they figure, I'll just grab that one from over there. People will remove them and then we lose. Then we would have completely lost all grounding to our top floor over there. Okay, let's talk about PMTs and LPTs. For those of you that have worked in residential work, you may have seen these going in. Now, sometimes the civil contractor, that's the contractor that goes and pushes around the dirt and the gravel and, lays out the roads and the sewer pipes and stuff. Sometimes they will go and install these. However, you as an electrician might also install these at times. You'll have to work with an excavator to get your excavation done right, but this is going to be a pad mount or a low profile transformer. And this takes the place of us having that pole with the overhead lines and then that overhead can mounted transformer. What's going to happen in this thing is ultimately when this is ready to go, BC Hydro is going to go and show up, and then they are going to go and drop a can on the top. You see these things are going to be green cans, or they're going to go and be tan cans, and they're going to be buried at ground level, and you see them just on the side of a cul-de-sac or something like that. They have that little symbol of the person, getting struck by lightning, falling over backwards because they got high voltage on the inside. You will always see a short section that's going to be hinged, and then this section that's over here, the back section, is going to go and have a transformer. So they can hinge up this section when they go and work on it. They're going to bring high voltage in, and then they're going to be able to take low voltage out to each of your individual places, the individual residences inside of that cul-de-sac. What we do is we supply one conduit. That's going to be the high voltage conduit. That's that one right over there. That is going to be coming from wherever BC Hydro is going to spec it. We are then going to go and take another set of conduits. We're going to run one out to every single residence inside of there. They're going to get one. In some cases, they actually require you to go and have two, an heir and a spare, so to speak, in case one of them gets damaged, so they've still got an alternate pull path. Other times, what they will require, and this is all going to be governed by hydro, they will require that you're going to run out sufficient for the number that are in there, and sometimes they want one or two just run out and then capped off underground, stubbed out, so that if somebody had to dig, and attach anything else, they would have one that they could attach into. What we do when we place this is all going to be bedded on gravel. So you're going to dig a hole, you're going to go and have gravel that's going to be placed around it for drainage. Then you're going to go and get this transformer base itself that is going to be craned in. You don't mold this thing, this is going to be pre-made. Almost everyone in the province, at least out here on the coast, comes from Langley Concrete Products. They got a big yard out there and they're an approved supplier. They mold those things and deliver them. So we get one of those that's going to be craned on there. What we do is we place around there this component over here. Now this is a heavy steel cable that is heavily zinc coated. Super stiff cable. You're going to run the thing all the way around the transformer base, and then you're going to run up the free ends inside, and you're going to deke them just out of those two corners over there. You're also going to go and apply a clamp. It is a big bolted clamp across over here to tie those together, and then you're going to clamp it to two separate ground rods. Be careful when you're driving these ground rods in that you don't drive them through your conduits. Know that you're going to have two front corner ground rods, so just make sure when you are running those conduits out that you don't have anything front corner. Otherwise you got to dig it up and repair it. It wouldn't be live yet at that point, but it would just be annoying. We run that around. We call this thing the counterpoise. What it's going to do is it's going to go and be in contact with the earth itself. It is also going to make sure that the whole area surrounding that is going to be safe. It's going to be at the same level because they're going to tie these ends to the transformer can. So if I'm standing over here, let's say that I'm standing over here leaning up against that one, I don't have any danger of being at a different potential than that. No induced voltages, nothing like that. These things are actually legitimately safe for your dog to go and pee up against. People freak out when they see a dog peeing up against. It's not nice for hydro, it's corrosive and stuff like that. But if they've been installed properly, they should be perfectly safe to go and be up against. The whole area surrounding this is then going to get backfilled. So what we have is then we place sand, not sand, we're going to place gravel that's going to go all the way around here. It's going to come up to about an inch from the top of that pad. So this whole pad is buried down quite a way underneath there. You're going to bury around the outside. On the inside, the level is usually going to be much lower over there. All the ground rods, all the counterpoise, all of that is going to be covered underground. That's a cool thing the first time you get to go and do one. Second time, less cool, 20th time you put one of these in, yeah. But, the first couple times you put one in, it's kind of a fun little project to get around to. Okay. Not much else to go and talk to you about that one. There is the depth, these things do have to be a foot underground. They're going to be covered with gravel to provide good drainage. And they do have to be at least 900 millimeters. That's going to be 3 feet from the pad itself. We do have to keep them circled all the way around. If there is excess length, you're not allowed to cut it off. The coil of heavy steel cable that you will get will be probably too long for what you need inside of there. What you're supposed to do with that extra length is just take that length and loop it like that and then stick a tie wrap around it. Bury that at the back end. It's the standard way to deal with excess length. Don't cut it off of these ends over here. You'll have to apply a couple of heat shrink boots over top of those ends. They come with the kit as well. And then when Hydra shows up, they drop that on there. They will pull in the high voltage lines. They will pull the low voltage lines. All right, lightning protection. We talked a little bit about that. The lightning rods that we're going to place on top of tall buildings, which are going to be a purposeful way that we are going to divert and run anything that is going to be discharged from the atmosphere down and through there. We do want to go and keep those lightning conductors away from other components because otherwise it will jump over. 300 volt insulation on NMD90 is nothing to that lightning strike. It will easily move across there. We do have to go and make sure that our conductors and electrodes for the electrical system grounding, we're not using them for our lightning rod system. That would then attract it down there. We have to maintain that 2 meter separation we talked about. And then the lightning rod system grounding electrode has to be bonded to our system one. We talked about that as well. And that bonding has to go and happen underground. All of that over there. Okay. Neutral grounding devices. Neutral grounding devices is going to be something different that you have never seen before. What we have done before is we've always had unrestricted current flow. Whenever we have a ground fault, and if we take a look at the review section that was placed up there, we followed through some of these fault paths. This is now a different fault path where what I want to do is I want to restrict the amount of current. Rather than me getting that amount of, 5 times, that's my target value, 5 times the current that should go and flow through that circuit. I mean, if this was a 100 amp, we would want to go and have 500 amps that we would be able to flow through that circuit. Underground fault, sometimes that would be too much current. It would be damaging to our systems itself. So although this is not common on single phase, there are very few places where it could be, but it is a requirement of the ITA that for harmonized electricians that you know about what these things are, just in case you run into them, so that you don't do anything dumb with these. They are going to have warning signs all over the place, but what they are is they're going to be a giant ground, or a giant resistor that's going to be placed into the grounding conductor itself. And that is going to go and drop my total amount of current that I'm going to go and travel through there, right? I'll actually write it out as the current formula. I is equal to E over top of R. So if I end up with a fault on the system, rather than me getting, up to 500 amps, the way that I would off of a regular unrestricted circuit, and my regular unrestricted circuit would be trying to return this thing back to my neutral, etc. What I will have is I'm going to, instead of bonding at the neutral, you'll note there is no neutral bonding that is happening over here. What is going to happen is I'm going to go and have all of my cans, that's all these dotted lines over here, they're going to be bonded down on this side of that resistor, on the ground side of that resistor. So that if I end up with any fault current, here's where we have the fault will then travel along our bonding path. It's not going through the ground, so it's going through cans and conduits, edges, and things like that, all the way back until it hits here, and then it's going to travel through that resistor back to the transformer. Now, normally, we shouldn't have any current that's going to be following that pathway. Now we will have some current that's going to be following that. We're looking at values of like 10 amps and under, because we're doing this for safety, so we don't get a big arc flash wherever this is going to be happening. Maybe it's a place that's going to be processing gas, or something that's highly flammable, dust, powders, and things like that. You can't just have these massive explosions because it's going to ignite everything else. So we've got to keep that power down. So this is down to 10 amps is going to be the size of my resistor. Most cases, that's what we're targeting. What I'm going to have is I'm going to have a monitoring device, basically an ammeter, that is going to be watching. Normally, there's no fault current, therefore it doesn't have to do anything. As soon as it does get fault current, what it will do is it will send a signal to the circuit breaker. It's going to be an electronically controlled circuit breaker. That circuit breaker would get the signal that, hey, trip out, and it will. It's going to trip right out, and it's going to take that circuit out so that we no longer have, dangerous current flowing or anything like that. These things can only have a single ground on the system, and our bonding, all of our cans and cases, needs to be brought back to that side over there. If I take my bonding back over here, up top, it would not work well, because then any sort of fault current would travel back along my bonding path and it would bypass that resistor, and I would see I'd have unrestricted amount of current. So all of your bonding is going to have to be downstream over here, and then this chunk is going to have to be an insulated chunk of wire. There are some specialty rules for this one. Don't stress too much on, I don't know if I've ever seen one of these. You probably haven't yet. If you are working in a hazardous location, there is a chance that you could have this. But there is requirements by the code that you are going to have warning signs up at the service, at the supply, telling everybody that this thing has got a neutral grounding device on it. All right, talk about testing. Grounds are supposed to go and be tested. The reason that we do ground testing is just because we need to maintain certain values of resistance to the ground grid itself. Now we know that the bond is where the bulk of our current is going to go and flow. However, we want to make sure that if the bond were to fail and the current were to travel through the ground, that we would still be good to go. Most houses, cul-de-sacs, things like that, we don't worry about this because it's all going to be low voltage. However, on high voltage installations, this is going to be a very critical thing. We are going to need to go and test these ones out. Over the age of a installation, resistance to the ground is actually going to increase because we are going to go and form what we refer to as rust or oxidization. That is going to go and happen. It could be on the copper, it could be on the zinc that it's starting to go and eat away the plate itself, and sometimes you actually have to replace your ground electrodes itself. Dry soil is going to go and change your ground resistance. You might have had a good installation, but then somebody decides that they're going to pave something, stick a sidewalk around the side of a house. I know for a fact that probably a lot of you have buried ground plates, real tight to the side of a house. And then they go and put a sidewalk over top of that. And what happens is all the soil underneath there over the next couple of years is going to get very, very dry. Dig up a basement sometime. If you ever dig up dirt that's been underneath a house, that dirt, for the most part, unless there's, sideways seeping of water, is going to be relatively dry, which means it would be poor conductivity inside of those. So anytime stuff has been paved over or concreted over, expect that's going to have dried out. If you have got areas that have got high mineral ionizations, ionizing types of minerals, or corrosive minerals, coastal areas with salts are going to be particularly corrosive as well, right? They're all going to go and cause, oxidization. So if we get a really oxidized plate over here, we end up with a lot of R across it. And if we would end up with any current that would travel through it, a large amount of fault current, particularly high voltage, then I'm going to go and have a lot of V, right? V is equal to I times R. So I'm trying to dump my fault current through this thing. In the case of a fault, there are times where we will get something that will flow through there. Not usually, but there are. I could get a large amount of voltage that's going to develop across it. We don't want to see voltage dropped over top of the ground electrode itself. Okay, if it would get too high as well, there's also a chance that you could just corrode this whole thing all the way out, and at that point, you have no ground in the system, and if somebody becomes that path, that's going to be dangerous for them as well. So let's talk about the actual testing inside of these. If I am going to be doing testing, it's going to be because it's mandated for them. Places like your communications towers that are mounted up on the top of mountains attract a phenomenal amount of lightning strikes. And as a result of those lightning strikes, you can get a lot of equipment damage. It's cellular communications equipment inside of there, so we don't want to see that stuff get, arced out. So we are going to want to make sure that there's a relatively good grounding pathway, both for the lightning down conductors as well as for the system ground conductors that are going to be inside of them. So during the install, there's going to be testing. They're going to go and document that. Then they're going to come back on a preventative maintenance schedule, meaning every couple of years, they're going to go up there, they're going to do this testing, and they're going to say, yep, the ground still looks good, or no, that ground is starting to get too degraded, we should replace that ground, find something to go and fix it up. Usually it's about a 20% increase. It doesn't matter what the resistance was. Some areas are going to be higher resistance than others just based on soil type, but if you get a 20% change, you're looking at a lot of rusting and oxidization. What we will use is this, that is going to be called my follow potential method. And what the follow potential method is going to involve is me putting a controlled amount of current through it. So this is going to be not just like a handheld meter, but you're actually going to have to plug this thing in because it has to source a bunch of current. So this is going to go and get connected. So it's got power inside of it. You've got 3 probes that are going to be off of it. One of them is going to go to the ground conductor and electrode under test. In order to do this, you would have to remove it from the neutral. So before you do that, you're going to put in a temporary ground. That's going to be this one over here. Drive in a temporary rod. It doesn't have to be the full length rod. It's going to be a shorter one with a smaller conductor. You're going to go and take this thing, connect it onto the neutral. Once that thing has been connected onto the neutral, then you disconnect this one. Once that one is disconnected, the actual ground electrode and conductor, then I'm going to connect on to my meter itself. I'm going to go and take another one, this C2. It's going to be called my current spike. And then I am going to go and turn this meter on. And what's going to happen is this thing is going to go and deliver a constant amount of current. So there's current that is going to travel through here. Obviously, as I'm really close over here, there's going to be a lot of current. Obviously, as I'm really close over here, there's going to be a lot of current as well. Because what we know is going to happen, the current is going to repel itself, and the current will actually fan out over top of its length. I should have drawn this one a little bit different as being more of a fanned out type of thing. But that's what's going to happen, is those individual electrons are going to fan out as they travel from there to there. So we get concentrations, less concentration, more concentration off of these ones. What I then do is I take this potential spike, and the potential spike I'm going to go and move along. There's going to be set, this to the electrode to here is going to be a set distance. It's going to be 10 meters or 5 meters, depends on the test that I'm running and what the manufacturer specs are. And then in between there, I'm going to insert this thing into the ground. And then I'm going to wait, take a reading. I'm going to insert into the ground, wait, take a reading, insert into the ground, wait, take a reading as well. And what it is doing is it is just sensing my amount of volts that I'm going to go and have at that point in relationship to what I have over here. Because V is equal to my I times my R. So I'm able to go and see how much current do I have based upon the soil resistance. It graphs it all. We don't have to do any math ourselves, but it's going to graph it all. And it's going to go and create something that's going to look like this. What we say the overall resistance is going to be wherever we are flattest on that curve. The resistance is going to go and drop away as I get closer and closer, and then as I get further and further away from that electrode, all of a sudden it's going to go up really far where I move out of that current path. Like if I were to move past this outside of the current path, we're going to see that rise over there. So we just read this thing at the flattest point over there. This needs to be documented, stored with site data so that you can go and check if you've actually seen that rise. Some of these, if you do have these type of transformers, LPTs and PMTs, in some cases they will actually require you to go and take some of these readings and make sure that they hit an appropriate level before they will put that transformer on for you. All right, that is the end of L1.